Hello everyone. Today we'll be going over section 1.3, which is going to be about real numbers and the number line. We have 4 objectives for this section. Our first objective being that we want to classify numbers and graph them on number lines. Our objective 2 tells us tell which of 2 real numbers is less than the other. Objective 3, find the additive inverse of a real number. And objective 4 is find the absolute value of a real number. So to begin, we want to identify a set. So a set is just a collection of objects. And in math, these objects are usually going to be numbers. An object belonging to a set is an element, and they are written between braces, so our curly braces that we have. So as an example here, we have our set of 1, 2, 3, 4, and 5. And the main thing to identify here is that because we have the numbers 1 through 5 in our curly braces, this is a set. We have a set of the numbers 1 through 5. And our numbers 1, 2, 3, 4, and 5, these are our elements. So these are the elements of our set. And each individual number, so 1, 2, 3, 4, and 5 individually are each one element. But so we have here just establishing kind of what is a set and what goes into a set. So our objective 1 here, we want to classify numbers and graph them on a number line. So just as a reminder between the difference of our natural numbers and our whole numbers, our natural numbers is the set of 1, 2, 3, 4, 5, and so on through infinity. And these are also referred to as counting numbers. Then our whole numbers are just the natural numbers in addition to the number 0. So we can represent numbers on the number line like below. So we have a number line here where we are beginning at this point. Beginning at point. And our first number we identify on this line is going to be 0. So this is our first identifiable number. Then what we have here is that we want to identify our natural numbers and our whole numbers on a number line. So our natural numbers, since we know, are going to be 1 to infinity. On this number line where we have identified here 0 through 6, we would say that 1 through 6 in this case, these are our natural numbers that are just identified here. And 0 through 6 would be our whole numbers, just identified on this number line. So we know that if our number line is going to begin with the value of 0, they can be our whole numbers. Well, if they begin with the value of 1, they can be our natural numbers. So our natural numbers are to the right of 0. But for each natural number, we also have a corresponding number to the left of 0 that are negative or the opposite of the natural number. This is just telling us that if we have the value of 1, we also have the value of -1. With positive 2, we also have -2. With a positive 3, we also have a -3, and so on and so on. So this is just establishing that for every natural number, there is also a negative natural number, or the opposite of that natural number. The natural numbers, their opposites, and 0 altogether form the set of integers. So integers are just natural numbers, 0, and the opposites of natural numbers, or the negative versions of natural numbers. So these integers would begin from essentially negative infinity, and you would go through until you reach some numbers like -3, -2, -1, 0, 1, 2, 3, on to infinity. So what we have here is just a more complete number line, meaning that we're just taking now into consideration the negative numbers. So integers are positive and negative numbers in addition to 0. So if we want to do a bit more of identifying here, we have this number line. And what we want to say is that any number greater than 0 is going to be positive. So we can draw an arrow. We say that these values are positive. While numbers less than 0, or to the left on a number line, are negative. While 0 itself is neither. 0 is not positive or negative, which is why we treat it as this kind of starting point when we want to identify if something is positive or negative. So our positive numbers are to the right of 0 on a number line, and our negative numbers are to the left of 0 on the number line. Then the last thing to identify in this case is our opposites. So our opposites would be our natural number and the negative version of that natural number. So for example, 1 and negative 1 are opposites. Then 2 and negative 2 are also opposites. 3 and negative 3 are also opposites. And this goes on for infinity in both directions, so negative and positive infinity. And these are opposites. Yeah, I spelled that right. All right, so these are our opposites here. So moving on, we want to identify that positive and negative numbers are signed numbers, meaning that when we write them, we can either write this positive or negative sign in front of them. So we would say negative value. So for example, -3 and our +4. Or into +3, whichever you'd like. But so when we write our negatives, we do want to include these negative symbols in front of them because we were identifying that this is the opposite of our natural number. And our natural numbers are not normally written with positive signs in front of them because when we don't have a positive sign in front of a number, we assume it's positive. But our negative numbers, they do have to have those negative symbols. Fractions, on the other hand, are rational numbers, and rational numbers are going to have a specific definition. So, with our definition given here from the book, we have this curly brace and we have an x, and then we have this line in between, and we're defining x to be the quotient of two integers with a denominator not 0, and that is the set of rational numbers. So when we read the part in the braces, we read this as the set of all numbers x, such that x is a quotient of two integers with the denominator not 0. And just as a note, the set symbolism used in this definition of rational numbers, where we have curly brace x with a line, x has some sort of property, and curly brace, is called set builder notation. This notation is convenient to use when it is not possible to list all the elements of a set. So when we can't list 1 through infinity, we would instead write out our curly brace x, and then we say where x is the natural numbers. And that's how we would identify maybe the set of natural numbers as opposed to writing 1, 2, 3, ... So all right, we use set builder notation if our set is going to be too large or too cumbersome to actually write out. So that's when we use our set builder notation. And the key to our set builder notation is just letting us know that some variable x has a certain property. And that's what our line is separating out. So we have that x and our property of x. So, since every number can be written as the quotient of two integers is a rational number, all integers, mixed numbers, terminating or ending decimals, meaning decimals that don't go on forever. And repeating decimals, so including repeating decimals, are rational. So now we have some examples of rational numbers here. So our rational number first, -5. So the equivalent quotient of two integers would be -5 divided by 1. Then for 1 3/4, the equivalent would be 7 divided by 4. Our rational number 0.23 can mean 23 divided by 100. 0.333 repeating, so going on forever, can also mean 1 divided by 3. And 4.7 is also the same as saying 47 divided by 10. So we see that each one of these numbers can be written out as the quotient of two integers. Now, to graph a number, we place a dot on the number line at the point that corresponds to that number. And this would be the coordinate of a point. So let's scoot down a bit here and do an example. So, once again, when we're graphing a number, we place a dot at the number line at the point that corresponds to that number, and this is the coordinate of that value. So, for example, we want to graph 3/2, 2/3, 0.5, -5/4, and -7/3. Now we have our number line here, but our number line is not defined. We haven't given it any values. But whenever we want to graph something on a number line, and our number line has no values, no beginning values or anything, it's always best to first identify 0. So we have this number line. Let's put 0 in the center of our number line. So there's our 0. Now let's make it so that every 2 boxes, or 2 lines ahead, is going to be one whole number. So let's say to the right, 2 boxes will be 1, the next 2 boxes will be 2, next 2 boxes will be 3. And then in the opposite direction, or to the left, we're going to say -1, 2 boxes, -2, 2 boxes, -3. All right, so we've now put numbers on our number line. So now that we have numbers on our number line, we want to graph the numbers that were given to us. So a helpful tip is often that we can change these values, since what we have here are a bunch of fractions and a decimal, is that we can change these all into fractions and mixed numbers. So let's change these. So 3/2 is the same as saying 1 and 1/2. 2/3 is a proper fraction, so we'll leave it at 2/3. 0.5 is 1/2, so we can say 1/2. -5/4 is going to be -1 and 1/4. And -7/3 is going to be -2 and 1/3. So we've now changed each one of our improper fractions and decimals into mixed numbers and proper fractions. And then we can graph these values. So it always helps to kind of change those values first. So beginning with 1 and 1/2, now we just need to identify 1 and 1/2. So 1 and 1/2 is the point between 1 and 2. So on our number line, there is a line there between 1 and 2. So we'll say that this point here is 1 and 1/2. Now our next value is 2/3. And whenever we're plotting things on our number line and we don't have maybe exact values, we can always estimate a bit on where something will be. So 2/3, we know that's greater than 1/2, but it's not quite 3/4. So when plotting 2/3 and we think to ourselves, this is definitely 1/2 and let's say this is 3/4, our 2/3 will probably go somewhere in the middle. And this is 2/3, oh sorry, 2/3. Now we also have the value of 1/2. And we see that 1/2 and 2/3 are going to be fairly close together. So we have here, this is 1/2. Then we have -1 and 1/4. So -1 and 1/4 is less than 1 and, or just less than -1. So when we write -1 and 1/4, it's going to be more left than -1. And if this value here is probably -1 and 1/2, -1 and 1/4 is going to be the point in between. So we have -1 and 1/4. Then lastly, we have -2 and 1/3. This value between -2 and -3 is probably -2 and 1/2. And -2 and 1/3 is less than -2 and 1/2. So let's place it about here. -2 and 1/3. All right, so we've plotted some values on our number line. Each one of these values that we've plotted would be our coordinates. So moving forward, not all numbers are rational. For example, the square root of 3 cannot be written as the quotient of two integers, and we call these numbers irrational numbers. So again, with our definition of irrational numbers, we have a set builder notation. So we identify x, and we say that x has the property that x is a non-rational number represented by a point on a number line, and this is the set of irrational numbers. So the decimal form of an irrational number neither terminates nor repeats. So this means that it's going to go on forever, but when it goes on forever, it's not repeating itself. It's just going to be multiple numbers on forever. So rational numbers and irrational numbers can be represented on a number line, and together they form the set of real numbers. So rational numbers with combination of irrational numbers are the set of the real numbers. And our set builder notation again here is telling us that x, when x has the property that x is rational or an irrational number, this is the set of real numbers. Then we have a little chart here, and this kind of helps wrap our brains around all these different sets of numbers that we have. So this entire square here is going to represent our real numbers. And our real numbers are broken down into rational numbers and irrational numbers. But within our rational numbers, we would include integers. And then within integers, we find whole numbers. And within whole numbers, we find natural numbers. So, also another example of a number that is not a real number is the square root of a negative number, such as the square root of -5. So this would not be considered a real number. It would actually be considered an imaginary number, but we won't get into that. So something like that where you can't actually find the value of the square root of -5, since no two numbers multiply by each other to get -5, that would not be considered a real number. But we see here that our real number, or a set of real numbers, contain sets of other numbers. It contains the set of integers, it contains the set of whole numbers, and it contains the set of natural numbers. So our real numbers here is going to be kind of our overarching set of numbers, and then when we identify certain numbers, we can get smaller and smaller here until maybe we can say, okay, this is a natural number because it is a number 5 or something along those lines. All right, so on to objective 2. We want to tell which of two real numbers is less than the other. For positive numbers, they are increasing to the right on the number line, so any number to the left of another is less than it. So we can say, for example, that 8 is less than 12 since 8 is to the left of 12 on the number line. And this idea is extended to all real numbers. So basically on your number line, any number that lies to the left of another number is going to be less than that number. So now we have our ordering of real numbers. We say for any two real numbers a and b, a is less than b if a lies to the left of b on the number line. Then we have our figure 6 here below, which we have this number line. We have a is to the left of b, a lies to the left of b, or that a is less than b. So this holds for all values. So if you have a number line, you can identify whether a value is less than it if it lies to the left of your original number. So thus, any negative number is less than 0, and any negative number is less than any positive number as well. So this is telling us negative numbers are less than 0, therefore negative numbers are also less than positive numbers. 0 is also less than any positive number as well. All right, so an example here is -4 less than -2 true or false? And we're going to identify this and determine if it's true or false based on using a number line. So once again, we have a number line here. It is not defined. We don't have any numbers marked on our number line here. But as always, we want to start with 0. Since we're working with negative numbers at this point, and we want to see if -4 lies to the left of -2, let's make 0 shifted a little bit right on our number line. This will give us more room for our negative numbers. Whoop. Wanted green. So let's say that that is 0. Then we'll say once again that every 2 boxes will be a whole number. So we'll say 2 boxes to the right is 1, another 2 boxes to the right is 2. Then, once again, starting at 0, 2 boxes to the left will be -1. 2 more boxes to the left will be -2. 2 more boxes to the left will be -3. 2 more boxes to the left will be -4. 2 more boxes to the left will be -5. All right, so we have our defined number line here. And now what we're doing is we're seeing if -4 is going to be less than -2. So let's say -4, we're going to underline this in red. We're going to mark this with a red dot. Our red dot here. And let's rewrite this to say -4 in red. Then we'll identify -2 with blue. So we'll put a blue dot on -2. And we'll also rewrite -2 in blue. We have our -2 here. And what we see here is that 4, or -4, is to the left of -2. So -4 is to the left of -2. And this tells us that -4 is less than -2, which means it is true. It's true. And so it was that simple just to see if a number was less than another number, using a number line purely to just see if it lies to the left. All right, on to our third objective here. Our third objective is asking us to find the additive inverse of a real number. For any real number x, except for 0, there is exactly one number on a number line, the same distance from 0 as x, but on the opposite side of 0. These pairs are called additive inverses or opposites of each other. Notice that these are called opposites, the same way that, and let's scroll up here, the same ways that negative versions of our natural numbers are also opposites. Because now when we talk about additive inverses, we're talking about the pair, the negative and the positive. Here we go. So these pairs of positive and negative numbers that are the same except for the sign, positive and negative, these are called additive inverses or opposites of each other. So, and we have our opposites here. Just like as before, we're identifying these values. And these values also have the same distance from 0. It's just that they're negative and positive. And these are additive inverses or opposites. And this can be for any real number and not just our whole numbers or integers. This could also be to say if we started making points at, let's say, -1/2 and +1/2. These are also additive inverses. So this is going to be for all of our real numbers. For all real numbers. So our additive inverse, or the additive inverse of a non-zero number x, is the number that is the same distance from 0 on the number line as x, but on the opposite side of 0. So finding an additive inverse, the additive inverse of a non-zero number is found by changing the sign of that number. A non-zero number and its additive inverse have opposite signs. So this is the point that we're trying to make when we say that an additive inverse of a non-zero number x is the number that is the same distance from 0 on the number line as x, but the opposite side. All that to say, your additive inverses have opposite signs. The same core number, but the signs are different. So we can indicate the additive inverse of a number by writing the negative sign or the negative symbol in front of the number. But this means that we can also get a negative negative. So the double negative rule tells us that for any real number x, if we have a double negative, that is just equal to the positive version of x. So some additive inverses we have here are going to be 7 and -7, 2/3 and -2/3, 0.52, and -0.52. So our additive inverses are the same numbers with different signs. And with our double negative rule, all this is telling us is that we want to find the additive inverse of, say, -7. We're just going to add that negative sign in the front. That would give us -7, which would give us +7. Now on to objective 4 here. We want to find the absolute value of a real number. Additive inverses have the same absolute value since they are equal distances from 0 on the number line. The absolute value of a real number x, written as, and we see we have these vertical bars that surround x, written as the absolute value, can be defined as the distance between 0 and the number on the number line. This just means to tell us that if we take the absolute value of 2, that value is still going to be 2. And if we take the absolute value of -2, that value will also be +2. And this is because distance is a physical measurement, and therefore it is never negative. If you walk 2 feet in front of you, and if you walk 2 feet behind you, if you're starting at that base starting point, you're walking 2 feet either way. The direction itself doesn't really matter. So your absolute value, you can think of it in that way. The direction doesn't matter whether you're going to negative or positive. The core distance you traveled is the same. So therefore, when we calculate absolute values of numbers, They're never going to be negative. Your absolute value is never negative. Unless, of course, there's a negative outside of your absolute value, then it can be negative. But we will show an example of that in a moment. So we have kind of our definition here of an absolute value. We say for any real number x, our absolute value of x is equal to x, so whatever that value of x is, if x is greater than or equal to 0, so if x is positive or 0, and it's negative x if x is less than 0. So then, by this definition, if x is positive or 0, then the absolute value is itself. Similarly, if x is a negative number, then the absolute value is its additive inverse. And technically what happens when we have these negative x values is we apply our double negative. We're saying that if x is less than 0, we would say negative x, which means that if x were, say, negative 3, we would say negative 3, which is a positive 3, which makes our absolute values of numbers always positive. So lastly, some examples here. We say that, for an example, the absolute value of 1 is positive, which means that our absolute value of 1 is just positive 1. Then if we take the absolute value of negative 100, we're applying that double negative rule. Negative 100 is less than 0, so we're saying negative 100. And this gives us positive 100. Then we have our absolute value of 0. And our absolute value of 0 is just itself, since 0 is greater than or equal to 0. And now we have a bit of a tricky one. We have negative absolute value of negative 5. What's going to happen here is that we will be taking the absolute value of negative 5, but now we also have to apply a negative because it is outside of our absolute value. If you would like, you can always add parentheses to keep these separate in your mind. But when we write this out, we have this negative, and now let's make some brackets here because we need to apply our double negative to our 5. So this tells us that we have this double negative inside of our brackets, which will give us a negative positive 5, which would end up giving us a negative 5. So our absolute value fixed the negative 5 that was inside of the absolute value bars, but that since that negative was still on the outside, we still ended up with a negative 5 as our answer. Then finally, we have a number like the absolute value of negative 2.57. Basically, we just have a decimal here, but the same rules still apply. We still give these double negatives here. So we get a negative 2.57, which gives us a positive 2.57. And that finishes up our lecture on section 1.3 for today. All right, so obviously if there are any questions at all, you can always feel to come by my office hours. And if not, I will see you on Thursday. So have a great day, everyone.